Hello, everyone, and welcome to today's webinar. Our speaker, Dr. Moshe Ben-Talila, has over 14 years of experience as the manager of VisiMix's customer support. He holds a BSc and an MSc in chemical engineering from the Technion, specializing in reactors design. He also holds a PhD in chemistry from the Hebrew University of Jerusalem, with his dissertation focusing on practical methods for scale-up processes in the chemical industry. Dr. Ben-Talila has extensive expertise in technological transfer, having worked as a pilot plant manager and project manager in an API company for over 15 years. Dr. Ben-Talila has made significant contributions to the field, including his involvement in developing a BSc degree program in pharmaceutical engineering and writing the syllabus for the Pharmaceutical Engineering BSc degree program at the Azrieli College of Engineering in Jerusalem. He is also a lecturer at the college, teaching reactor design and principles of fluid mechanics. In today's session, we are very excited to discuss the upcoming release of our new product, ChemViMix. This innovative tool enables users to simulate the dynamics of chemical reactions in tanks with non-ideal mixing. Feel free to ask any questions in the chat box during the webinar. We will do our best to address them either during the session or via email afterwards. Enjoy today's presentation, and without any further ado, I'll hand over the microphone to Dr. Moshe Ben-Talila. Enjoy.
Okay, thank you very much, Marcy, for your introduction, and thank you very much, everyone, to be here with us. We're very excited to provide to you a new VisiMix product and really a new capability that is trying to connect the molecules to the hydrodynamics in models that will be real models and will be representative to the connection and the influence of the mixing in the process. In this case, we'll talk about multiple reactions that always happen together in a tank. Of course, we have main reactions and secondary reactions, but we will be able to apply any one of them and understand what will be the influence of the hydrodynamic we are providing to our process to generate results. So thank you very much to be with us. If you have any questions, please write your question, because we are here many people and it's not possible to open the microphone to everyone. So what we'll do today, we'll present ChemViMix, is chemical with VisiMix environment, VisiMix and mixing, all of these together, coordinating one place after a long time to try to solve these kind of problems. We finally get some way to model it and to generate results. What we'll do today is we'll, of course, some words about VisiMix, people that don't know VisiMix and joined us now. We'll talk about the motivation and good mixing, and we are refreshing again what is mixing, how to attract mixing problems, and what is important to do when we are talking about scaling up, how to apply VisiMix, ChemViMix when we have a reaction we need to scale to the next step, or to transfer to the technology, or to design a new equipment, or to control that the new equipment we are getting from some designer will be good to our process. Always the equipment normally is good, but the question is if this equipment will be good for our process. Is a real question that we need to answer. Is in our responsibility to respond to this question, because we know more about our process and our project than everyone. We have all the background, and the best way and effective way to answer this question is to perform some calculations that will connect between the process and the equipment, generate an answer that will be representative. In this presentation that we will share with you, we have the description of all the products. If you want to have a tailor-made presentation for your company, please contact us and we will provide a presentation about the company, and based in your case, in your field, we'll be able to run the software according to your specific applications. Okay, so for people that don't know us, VisiMix is a unique software because it's based in semi-empirical models. We connect and calculate the velocity by the solution of momentum balance. In order to be sure that these results will be representative, we characterize every momentum component of the momentum balance in the integral equation and in the differential equation in order to generate the main question in fluid dynamics, that is the velocity. With the velocity, we're able to calculate different kinds of parameters. First group of parameters will be hydrodynamic parameters, mixing parameters that are basic parameters like power per volume, energy of dissipation, or power per volume distribution, mixing times in different levels, macro mixing time, micro mixing time, shear rate, eddy size, all the parameters that are characterizing the flow. And those parameters normally will control the operation that we are looking for. That can be a distribution of solids, mass transfer coefficient, gas holdup, and the news is that we will be able to upload many reactions, reversible, non-reversible reaction, catalytic reactions, and calculate what will happen with my process in the complexity of mixing we are generating in our tank. This is the news that we are applying. But the idea is by using the main fluid parameters and how will be the influence of them to our reactions in the tank. Everyone can use the software. It's simple to use, feed data, generate results. You don't need to be expert on simulation or on modeling. What you need to understand, of course, is what is the meaning of the results. If you are familiar with this kind of parameter that I mentioned before, that the first group of parameters, you will feel comfortable. If not, part of our customer support is to provide to you all the knowledge, how to feed data, generate results, and what is the meaning of this result. What is the meaning of energy of dissipation, micro mixing time, shear rate, microscale size, all of those parameters that are really characterizing my flow and my mixing in the tank. The software is used in many companies in all over the world during many years. We're in the market around 25 years, and the companies working with us, and once they have a good idea about this connection and the importance of this connection, of course, we continue to work with everyone. I'm very happy to salute our customers and to be happy to continue to work with them. The technology was developed in Russia, the first models of mixing. When they came to Israel, we transferred this in products. Professor Leonid Draginsky, in this stage was Dr. Yuri Kokotov, Roman Seidman, and the other people in the company that really solved this very complex problem about reactions and hydrodynamics. The summary of the history is that we are solving in one hand momentum balance. We know the velocity of the flow. In order to be precise, we use known theories of mixing, but we apply and we modify a little according to our experimental data to the geometry that we are using, that it is stirrer vessels or pipe. We will release in half a year a pipe that will be flow chemistry. But we are transforming the general theories to a specific theories because, as you know well, the geometry is really influencing the flow characterization in our process. So in our case, our geometry is or a pipe. It will be in the next step. In this step is a real normal stirrer vessel That is a normal equipment we are using in many companies, in many fields in order to process, to manufacture our materials. So we adapt these theories to the specific geometry. And once we know the velocity, if you provide more data, we'll be able to know about the influence of this hydrodynamic in the process. For instance, the distribution of solids, we will require the concentration of the solid, the particle size, and the density of the particle. For the reaction, we will require a good or starting point kinetics of the reaction that you can obtain with different equipments, and you can run in a very typical laboratory where you are taking samples of concentration of the material as a function of the progress of the reaction. It will be enough to have some starting point coefficient kinetic coefficient and the power that is normally representing the reaction rate. That will be required some first starting point in order to understand this interaction between the reaction and the process. The VisiMix company, as you can see, we have from 1995 until now, every 2-3 years, we are releasing a new software. So now we will write a new line that will be from 2022 to 2023, a ChemViMix that will be a chemical reaction in mixing in VisiMix and VisiMix. Companies working with us in different fields that you can see working, and we're very happy to provide them. Are only fields that we are working with companies. And Dr. Victor Atiemo Bank that is with us here, and we're very happy to have you with us. Is always helping in the community to understand process in a good way, in a very simple way, and to connect between all the chemical engineering knowledge that we have, and is always reminding us how to progress. So thank you very much to be with us, Victor. And he advised to use the software and to progress, to improve the process performance in companies by doing simulations. We have many companies working with us, about 250, and we're very happy that you will come to us and start to generate new connections and results for your company. Okay, what is the motivation of the use of mixing in reactions and in general in process? The motivation is that we know that the company is asking us about to progress to the next step, and the idea is that when the company is coming to ask what will happen when we want to go to scale up and to design, we will we need to answer this question. Of course, we have many questions, but the main important question will be what will happen to the next step. And when we evaluate it, we know that the main change is coming because we are changing the size or the geometry, and this influencing directly the connection between fluid elements, so the connection between the materials in our tank, and a light deviation from this interaction between fluid elements that happen in the tank can generate different results in design, operation, and purity and quality. And it's our mission to answer the question. For this, if we are catching the main parameters and we are evaluating it, we are able to establish them even from the first step, that it is the lab, small equipment. And if we are catching this information and understand at the beginning of the way what can be the parameters that will influence the process, will be able to help people in the design, the production, and generate new results. When we talk about what is good mixing, because we are service, the main important answer will be that we are providing service, and mixing is not something that is separate from the process. It's opposite. The process is the main idea, and the mixing is the support. So we are supporting the process, and for this we need to understand what is the meaning of the process. So as I showed before that, only to remind, I have a very interesting example about a company that for some reason wanted to install a new equipment and design a new equipment for an existing process. And they, after they installed the equipment and they designed all, they found that the process is not running well. It was a reaction in a liquid solid phase. The solid was there a chemical, and another reagent need to react with this chemical, and they found that they have some deviation in the results. They have no good quality after they change the equipment, install, and it's not working well. They wanted to find what was the reason, and when they find the main reason, it was very surprised. Why? Because the assumption was that because you have solids, you need to have a very good distribution of solids. And once they calculate the distribution of solids, they found that the distribution of solids was very good in the new equipment, but by surprise was very bad for the process, because they accelerate a connection between the material, the bits, and the heat space that was their quantity of oxygen, and this oxygen hydrolyzed the material. So in this case, when they wanted to design equipment that will be good by providing homogeneity of solids, they generate bad results. So the idea is to understand that we need to connect the process, the mixing with the process, by when the mixing is the service. We need to ask the process what is required and find the conditions that will generate with the mixing to provide the process the conclusion. This company get the conclusion that they need to have a coordination of all this knowledge, and they lose 6 months, and the $1.2 million was not good for them because the design was not enough good, so they needed to design again. So this is an idea about what is good mixing. So not always homogeneity will be good. It's depending on the process. This is a case that you can see here a better flow patterns, and the solids were in the flow patterns. You see here more in the top than in the bottom. In the older equipment, they had better situation. The solids were moving in the bottom, nowhere well distributed, but good for the process. And this is something that is surprising, and we need to take care always to think about it. Based on it, the best idea that we explain to you sometimes is that we need to find a way to, during our growing of the process, we will understand that we have other phenomena, that is flow and mixing, that is part of the phenomena that happen in the tank. So when I was pilot manager, we did some job about it, and the main way to work, or the best good way to work is to understand the process in the lab, and calculate with the software, or know what is the flow you are generating, and set up the same kind of flow in your tank in the way that you are bringing your process with the conditions you will provide in the next step, and based on it, you will be able to find some solution and get some model that explaining your process. So this is the background on the main idea about how to think about mixing in few words, only to remind you about what we were talking. Now, what is VisiMix, ChemViMix, chemical reaction and kinetics? As you can see here in this scheme, is that we are feeding molecules in our tank, and because we are generating some kind of movement and interaction between them, that will be different for different kinds of equipment, we will be able to understand which kind of conditions will generate a reaction that is good for me in the process. So we are connecting between the flow inside and the molecules that are interacting in different places. So the field of application of the program, the software input supports a convenient format for engineers entering chemical kinetics that normally you can get from a simple experiment that taking concentration as a function of the time during the process in a batch, in a stirred vessel that are very known in the industry, and allow user to analyze the effect of inlet point position, chemical composition in the inlet flow, and mixing design and more. The steps that we're talking about are the following. We are using a design characteristic of a reactor, like we did a normal VisiMix that you know, customers, and you will see now. We'll calculate two main points. The first, we will use rotational, radial, and axial velocity in the tank. The second, we will use the local mixing. So we will not only calculating the integral flow in the tank, we are taking in consideration the local mixing, the turbulent eddy of dissipation that will generate zones that are characterized by different levels of microfluid elements that will be the main components of the reaction and mass transfer. Based on the primary characteristics of the first part, okay, the velocities in the tank on turbulent flow generated in step 8, obtain the secondary flow characteristics, which govern macro scale and micro scale into the tank. So what is the main news? That we're including the micro fluid that happen into the tank as a part of the consideration of the mixing and the reaction or the material interaction to generate the reaction in the tank. This we are doing. And finally, obtain the local concentrations of reactant based on both the hydrodynamics and the secondary mixing. And once we have it and we have a complete characterization of the concentration as a function of the time in batch, semi-batch, or continuous, we will be able to scale up, because once we know it, is like, again, we know the flow in the tank and we know the results we will get with the chemistry. Only to remind you, macro mixing time in VisiMix is defined what is the time required to generate homogeneity in the level of 99%. It's like, in the intuitive point of view, we are taking balls that are black and white, we are moving our tank and we are putting our balls black and white, very well distributed. The micro mixing time is a completely different issue. We are talking about the micro scale that we are generating in our tank, mini tornadoes, and we are asking how long it's taking to converge in the same place. So in simple words, on intuitive point of view, is how long it will take my material, if we have balls that are black and white, to be gray. This is an intuitive point of view. We have, of course, a complete theories about turbulence, eddy size, energy dissipation, and cascade of energies. All of this we are taking consideration. But in simple words, we are talking about these two main important parameters that we are using both inside the tank in order to evaluate the concentrations of our materials at the positions that will be important for the process. What we will see when we are calculating this kind of thing. In very fast reactions that we know, and this very typical reaction, we can have a tank with water, and when we feed Ki, KiO3, and NaAC, and we mix these powders, we got a solution that will be, all the materials will be soluble, all of them are salts, so they will be soluble. When we feed HCl, if we are spreading well the HCl, we will generate NaCl and acetic acid that continue to be with no color. But when we don't spray the HCl in a good way, we have a high concentration of HCl. My result will be iodine, that is some color in my tank. And these results can be good or not good depending what we are looking for, okay? But we know that the same kind of material with different kind of operation maybe will generate different results. The reaction you have here in the bottom, what is the redox reaction, okay? Now, what we'll see, 1 minute please. What we'll see there is the following. We have this video in our website. So you can see here the reaction again. And what you will see when you are feeding your materials, okay, in your tank, in the tank, okay, we have here the materials in our tank. You see all the materials here. And we start to see what happened inside. What will happen here is we are feeding the HCl without mixing in order to show what are the eddy size, what are the difference of colors, okay, without mixing, okay, only to show what is really happening when we feed some material or some plant and eddies moving in the tank. When we start to feed the material from the top of the tank, you see, because there we have no very good micro scale parameter, you see that we are generating iodine in the top of the tank with a very big plant, and in the normal VisiMix you can see the blending. So you will see the blending that will be, of course, according to our results. Now, when we start to feed close to the impeller but low velocity, what you see here is some plant. We have no strong plant, but we see color in the tank. The meaning of this that we are improving the strength of the HCl in the tank, and now we will able to generate good results. Now, when we start with high velocity and we are feeding our material, we will not see this plant because we spray the material well. This kind of experiment is simple to do and it's really connecting between reactions and concentrations in different kind of mixing environments. In our approach, we will be able to feed every reaction, as you can see here, with the stoichiometric parameters, with the K, that it is the kinetic constant reaction, and A, alpha, and beta, that are the order of the reaction. And we can have a complete group of materials that we can define and add in some database. This is new too. We'll show to you a different interaction that it is more new one, and you will be able to have database for reaction, the database for materials. And of course, you can change the conditions according to the process. What you can see here is now the implementation in the flow chemistry that will happen in around 6 months from now or 9 months from now. And what you will get is the concentration as a function of the time or a function of the position, depending on the application. Okay, now what we will do, I will open the software and will solve the new software that in this step is only a demo. And I will feed the reaction A plus B giving C, is the main reaction, the second order reaction. The A will be in the tank, the B will be the feeding material, and this B knows how to react with himself and generate a material that is D. The feeding position we can change, and what I will do now, will open the demo of the software to show to you how is the presentation of the software and how is the input data required and which kind of result we will be able to generate. Okay, so the software, as you can see now, is a demo. For this reason, we don't have an icon now. But if I open the software, you see it's a little different than we used to have in VisiMix, because we are using a new platform. In this new platform, we are divided the zone in three. The first zone will be the projects that will be open. The second zone will be the mixing parameter that we'll be able to calculate. In this step, in this product, will be all regarding to chemical reaction in mixing environment. In this main part of the frame, we will get the response, the solution. In our case, will be concentration, the portion of the time against a well-mixed equipment. So we will present two graphs always, the results for the assumption that we have a well-mixed media, and what is the result when we have a real mixing according to the parameters. And in the rest of, we will be able to send our result that we are interested to save, to keep in mind in the desktop, and from there we will be able to generate a report. In our case, if I click project new, the software will start to ask me the name of the project and the main important windows that you know in VisiMix. Okay, but what I will do, because it's only a demo, it's not running all the windows as we want to show. What I will do, I will pass through every window through the edit input. For this, I will open a project that is ready. Okay, as you see here, we have a database of all the projects we are working with the software here. So we can define a project. Inside will be VisiMix files, and you can have it organized directly in your computer. It is new. Now, when I click the name, in this case is test, it will open for me the project. Now you see test here and test in the main window. Here, what we'll see results. In order to understand what are the input parameters, we need to come to the sequence that we know from VisiMix. It will be automatic. Once we give the name of the project, the software will start to ask me the tank, the buffer, the impeller, the fluid properties, and other parameters for the reaction. Okay, so the first, you see the tank. Now, different in order to save your time and get more less windows, we are condensating all the data required for the tank in only one window. So you see, you can choose every tank or with jacket, and you can give the data from the tank. In this tank, we have the diameter 1,600, the height 2,000, the volume of the complete tank is 3.7 cubic meter, and the actual volume that we are using for the mix for the reaction is 3,000 cubic meters. If we have jacket, we can click jacket and we can give the height of the jacket. Okay, when I click OK, the software will open immediately. Okay, you have buffers, so we include the buffers that we know with the dimension of the jacket of the buffers that we have for our project. It's four buffers. It is a complete buffer jacket, a tank. We have the width of the buffer. You see the buffer here. The width of the buffer, okay, this parameter, the distance from the wall, the distance from the bottom, okay, and the angle that continue to be the same frame. You have here the buffer, here the wall, and the angle will be zero. If we continue to fit, the software will ask me impellers. In this case, we have pitch pedal. I will show you after that we have a new impeller that we implemented here, but here we have the input data. This is the 500, the pitch pedal, very typical one, as you can see here with the dimension, the main diameter, pitch angle, blades, and all required, and the velocity we are using. We can have more than one impeller, all that we know from the software. Now, we finished to feed all the data about the geometry and the operation. Now we need to feed the data about the physical properties of the media. Again, in one window, we have the density, the viscosity, and it will be power law or rule. We can change according to what normally we're doing. In this case, if you click save to database, you can save the name of this material. So it's very convenient now because you don't need to again feed data. It is really, you will select your material and it will appear here immediately by load from database. Okay, now if we come to understand better the mixing part, for mixing, we need to understand that in order that the process will progress, we need to connect between two materials. Yes, we have A and B, and the opposite, we have B and B that will generate an impurity. But any reaction will occur when two molecules will be in proximity and will meet one to the other one. For this, part of the way that we are able to calculate the actual mass transfer into the tank is that we need the molecular diffusivity of the materials. The molecular diffusivity for typical material, when we click here, we give some number, and this typical material will be enough good for you. We can calculate more, and for this we will add here some guideline about how to estimate the molecular diffusivity. We have it in the software, if you remember well, when we want to dissolve some material, we are asking you, if you don't know the molecular diffusivity, we ask the molecular weight of the solute, of the solvent, and the temperature working, and from this we have some good idea about what is the molecular diffusivity. But it is the order of magnitude, very typical one in liquid phase. And now, what will be very important to know is how and where we feed. When we click the inlet and outlet locations, you see that we define two main input positions. The inlet one will be in the radius that is very close to the wall. Okay, you know that the distance from this is about 800, so 750 will be very close to the wall, and the eye is very close to the top of the tank. It's like we're feeding from the top close to the wall. The other inlet is here, you see here, is very close to the bottom in the wall, but we can locate at any place this point. Okay, we can put this material here if I change the coordinates. And for processes that we have continuous flow outside, we can define the outstream place for the flow outside from the tank. And we will calculate, of course, the continuous flow and the concentration in the outlet in the real mixing conditions, and not if we assume that it's a well-mixed tank. So we define where are our inputs, and of course we can define 0 and it will not happen nothing, or we'll define that maybe we have not inlet flow rates. And now we can select if we are working in batch or semi-batch. So I work or continuous. When I click inflow rates, batch or semi-batch, we are defining, you see, inlet 1, the flow is like this, okay? And we are feeding for 1 second, 10 seconds. The inlet 2, we are feeding for 30 seconds here, okay? And we can calculate, we can change every one of them. And now, as you can see, as you can understand well, it's like we're doing batch, okay, very short feeding material, okay? Time. And now, the other point is that we can have the database for all the materials. So we can find here the materials. We define which material is entering on every flow and what is the flow for every reagent. Okay. Once we define all of them, you can see here A is entering from here, B is entering from here. Okay. We define it that A is batch and semi-batch is taking a little long time. And we define, of course, the main product and the byproduct. It is C and D. And once we have all of this ready, we can we can add the reactions. As you can see here, we have reaction A, reactant A plus reactant B not ending main product, to reactant B provide me a side reaction. If we click edit inside, what we see is the reaction and the reaction rate, that it is the K and it is the order of the reaction for A1, A2. The numbers can be any number you want. The coefficient can be any coefficient you want. And you can, in this case, we define the reverse reaction. 0, the meaning of this, we are not progressing with the reaction. We can have catalyst and inhibitor. And when I will click here, we will see some consideration of reactions that are taking consideration catalyst in the process. The same for the site reaction. You can see this is the order of magnitude of the site reaction that is entering in the second place. When you see this green color, the meaning of this that you are feeding the data and is well evaluated, and the V, the meaning of this you can continue to work with the process. And once we finish to do it, we can calculate immediately. For instance, in the batch, I want to know what is the composition as the function of the time. When I click there, it asks me what you're looking for. You're looking for A, for B, for the main products, for the byproduct. Let's say I'm looking for the byproduct, okay? You see immediately that in perfect mixing time, this will be the byproduct. In our real mixing time, this will be the byproduct. So we are talking about concentration in mole per liter. So in the perfect mixing, we have low impurities. We have 0.05. And in our real life, we are changing to 5 times more. Okay? But we have connecting between them. We can copy this to desktop. And what will happen, if there will be no demo, that this will appear here in the desktop as a list of results that you are interested to have, and after that to compare, to send to every report. We can calculate again in batch the final composition, and you say immediately what is happening when we are talking about a perfect mixing tank, that it is well mixed tank, and what happened when we have an actual mixing tank. As you see immediately, what is the difference? You are not converting your material as you wanted, okay? If we fit one, we are getting only 75% conversion, here 87%, but it is the real life. So we will not confuse ourselves now. We will get more than we expected. And we have the main reaction and the side reaction. And again, we can copy to the desktop and continue. And in this way, we'll be able to work. The same, we can do it with we can do it with semi-batch if we select a semi-batch final results. So this is the main point. And the main point is to understand that now we really, by understanding the mixing in all the levels, fluids elements were generating, interacting in different zones, taking consideration every zone, implementing the continuous, the main flow of the tank, and feeding some estimation of the reactions that normally you are able to get, we will be able to provide in a click a comparison between what will be the mixing environment in comparison to the well-mixed tank, and in this way to answer in a simple way materials, components, weights, yield directly and not by some abstract mixing parameters that the audience are a little more difficult to understand. We are really connecting the real environment and the main reason for the deviation when we're transferring the process from one side to other side to the material. How much material I will get, what will be the destination, the deviation, what will be the order of magnitude of the deviation, even if we're not exactly the reaction rate, but we're able to provide in a good way. Of course, this is a demo. The complete software will be more automatic and will able to change parameter in the same way that we change normally. For instance, if I change now my high here, instead 200 will be 400. Okay, it's supposed to change. In this case, we are not. You see, we change it, and we'll click OK. We can ask now to calculate the final composition. Now, in this case, it's not changing dramatically. Again, not all the processes, the software is complete to show. So this is what we wanted to show. This is really new. The interaction with you, the software interaction with you, the screen is a little different in order to provide to you more capabilities to connect between the projects and the results and to compare between them. And this environment, we will, of course, implement more and more in our next products in order to give you capability to, for instance, run a complete connection between the RPM and the result of the reaction. So we'll ask the software to change the RPM from 100 to 500 by step of 10, and we'll generate the result, this table, and this result will be immediately exported to a complete summary table. This will be possible now with this environment that is new for VisiMix products. So thank you very much to be with us. We have some questions here. Let me only answer some questions. Of course, all the environment you can see is now more available for people that are working in the lab, because reactions, we know the capability to feedback about the reaction is more common to what we are normally used to have in the lab. And in this way, every chemist will be able to answer about what was the environment he provided to the process in the lab. And the connection with people that will transfer this process to the next step, to the next facility, will be more straightforward, because they were talking about the same base, and some base that is very is very common for every people that working in the synthesis, in the chemistry in the lab. A question from Cliff. Thank you very much to be with us. It is not quite clear to me on which parameter reflect the difference in solution between scale. Say, from 400 liter to 4,000 liter vessel to reflect the non-ideal effects. Yes, of course. When we are working on 400 liter or 4,000 liter, the mixing parameters that are controlling the reaction are the flow in the tank, so the macro mixing time, and the micro mixing time. When we are changing the equipment from 400 to 4,000, the energy dissipation around the impeller and in the bulk will be a little different. And the flow, the mixing time, the macro mixing time can be different. Okay? Because those two parameters are not coming from the same phenomena, normally we're not able to combine both of them will be exactly the same. But because we know how is now the micro mixing time influencing the reaction, once we calculate this in the software, we'll be able to differentiate the results, because we know the connection to the local mixing tool, and not only with the macro mixing time of some well-mixed equipment, that for well-mixed equipment, of course, we will not see any difference, okay? All the equipment will provide the same result, because we are assuming that it's well-mixed. In this software, we'll be able really to know and to feed many reactions, not only one reaction, secondary reaction. We can feed many, and with 4, 5, 6 reactions, everyone with the kinetic coefficient and the order of the magnitude of the reaction and generate the result that I showed to you about the final concentrations or about the real results in comparison to the well-mixed results. Okay, so thank you very much to be with us. If this is the step now, we're supposed to have the final version around September. We will release in the press and in the web and in LinkedIn. We will release the time that it will be available for customers. I will generate a new webinar that will only work about how to operate the software, because it will be like a tutorial, pre-tutorial webinar to most of our users that are dealing with reactions. They will like to know how to work when we will provide the software. So we will generate this web in order to generate some kind of training for you that we will save in our website. And after this presentation, as normally we are doing, some days you will get the presentation and the video of the software of the presentation that will be in our YouTube channel that you are invited to visit. So thank you very much. We have 2 more questions here. Sorry. How does its software take into account micro-mixing time in the reaction kinetics? We are, what we are doing internally is that we are solving the equation that is the mass transfer equation. If you remember, when we described the Reynolds transport theorem theory, they have some general equation for every parameter or for every characteristic that you can transfer. So we are writing the differential equation about mass transfer, and once we have there the velocity, instead the velocity, we are feeding what is the mixing consideration. And this will take us the mixing eddies, the velocity of the eddy, the macro mixing time, and the capability to generate results for how long will be the material connected according to the turbulent theories. We hope we will have this in a paper or some explanation inside the software once we will release in 2-3 months. Can you unmute microphone? It will be difficult for me because we have a lot of people here, but please write your question and we'll answer. How we can find VisiMix Chemical in VisiMix website? Okay, of course, it is new. It is the first time that we are announced. It is like an announcement. We're announcing you that we have a new software. All this information will be uploaded now after this website in our website by the presentation and the video, and our YouTube channel. Once we will release the complete product, it will be part of the products that we have in our portfolio in the website. And if you want to have a meeting and to show to you directly or based on your typical processes, we're very happy to do a tailored presentation for you. Thank you very much for everyone that was here. We have here many customers that I'm very happy to see. So it's a pleasure to me always when we are doing this kind of webinar to see you even by name in the list. And I remember every one of you I remember well. So thank you very much to be with us. We're very happy to continue to progress and to release new capabilities to try to help the industry, and of course our very good and appreciated customers to progress in their activities. Thank you very, very much for you. Bye-bye.